The value of a new Nimbus 2000 decreases according to the model V of t equals yada, yada, yada. I can start comparing it to what I have already in terms of like, what do I know these equations to be? So I can start comparing like, what are the pieces here, right? So I've got this parentheses raised to an exponent. My input is t and it's in the exponent, so it's an exponential model. It looks like I have a base of a, so a is 0.72, k is this value up here, plus a number is going to be my c. It doesn't look like I'm multiplying t by anything, which happens a lot, that more often than not, we don't have an r, but if we do have an R, it will tell you that there's an R. So we'll talk more about that later. But it looks like we don't have an R in this case, or really the R is 1. But we do have all of these other pieces. So V of t represents the value in galleons of the broom after t years after it was purchased. We're going to find the original purchase price of the broom. So an original purchase price indicates in this case for our values of V is value, T is time in months, always an important thing to do. So if we're talking about original in terms of these variables, that means that T is equal to 0. At the original means, okay, no time has passed, right? So it's good to ground yourself in the variables and ground yourself in the context. And what does it mean to be original in this context? That means that time was 0. Okay, so V of 0. Now, keep in mind that we had a formula that we put on the opposite or the page behind this that told us how to find the initial value or the original value, and we're going to see why it's this way. So if we plug in 0 for t, that's going to be 39,000 times 0.72 to the 0 power plus 1,000. Anything raised to the 0 power is just what? Anything raised to the 0 power is just 1. So keep in mind that that 0 power is only applied to this immediate neighbor. It does not get applied across the way. So that's 39,000, oops, sneaking a 9 there, times 1 plus 1,000, which is really just 39,000 plus 1,000. So this cancels out and becomes a 1 to leave us with just 40,000. Now, remember that the initial value is K plus C. And that's a new thing that we're trying to like kind of build off of what we've done so far in this unit, where we've talked about the fact that U sub 1, right, that first term, the initial term is the number in front of this changing piece. And that's just not the case anymore if we have a plus or minus. The initial value is this piece right here plus this piece. Initial value, y-intercept, right? So I can tell you right now that I know this is a decreasing exponential function. So based off of what we did before, that's what it looks like. And I know that the y-intercept, the initial value, is at 40,000, right? So these are all important things to keep in mind. What does this look like visually? What am I finding? What does this mean? Making all of these connections between the different perspectives is how you become a better math student. Interpret the meaning of the value 1,000 in the model. So 1,000 is this plus piece right here. This plus piece right here. And the plus piece is the horizontal asymptote. It's something that we haven't really played around with yet in terms of exponential modeling because we haven't done plus or minus anything. But there is a horizontal asymptote and it occurs at this plus piece, and that's at 1,000. So if I go back to my graph, that means that there's this line at y equals 1,000 that this graph will never go below. If I want to interpret this in the context, to interpret its meaning in this problem, that means that the graph will never go below 1,000, which means the y value will never go below 1,000. The value of the broom will never go below 1,000. Galleons. Technically, it would also never reach 1,000, but this is something that we talk about in terms of when mathematics technically is correct, but in application, it ends up being slightly different, right? If I, a classic example is that if I put my coffee cup on the table, it'll eventually hit room temperature and won't go below room temperature. Now, the horizontal asymptote for that exponential model will be the room temperature. Which we'll see in later problems. And so technically your mathematical answer is that it will never reach room temperature, but we know in the applications of this, that's not true, that it will eventually reach room temperature. But the way that we had to set up the model to describe this behavior, we said mathematically that it wouldn't ever hit zero. So this is when we have to kind of walk the narrow line or include two worlds into our mathematics, is we have to realize what it's saying mathematically and also know when that's just whatever being mathematics and it's not true in reality. I don't know if I'm making sense. I hope I'm making sense. If not, call me out on it and say, Miss, you were not making sense on that video, and that will be fair. Okay, so we're going to calculate the value of the broom when the value of the broom will be half its original value. So notice what it's asking you to do. This is a great prepare step. Calculate when. I need to find when. When is what variable? When is time? Time equals question mark. Okay, I need to solve for time. When the value of the broom, value, that's my V, is half its original value. We found the original value up above. So half its original value. This is a classic exponential model question. It should just take half of the original value and okay, half of the original value is 20,000. So I need to find out when it's going to be worth 20,000. So I just set it equal to that. Now here's where you could use numerical solve. If you don't have numerical solve, you could also graph it, set this equal to y, set this equal to y, and find when it's equal. Use some of your context here to help you determine the window to be able to find that intersection. That's always the key. T, we get to be approximately 2.19, and our time is in terms of years. And so that's 2.19 years. And years can be a decimal, as we've seen in the past, so that's totally fine. Okay, example 3. This is all just interpreting, as we can see at the top, interpreting exponential models. These are all classic questions that get asked around exponential models. So I just want you to get used to what all these pieces mean in the problem. So when you have things like write down, you're like, why are they telling me it's super easy? Why are they telling me it'll be just like quick? I can just write it down. And you'll know it's because of what these pieces mean in the exponential model, which will also help you when we get to our next piece, which is when we have to write exponential models and create them. The amount of electrical charge C stored in a mobile phone battery is modeled by this equation right here. We can see that it's increasing. When I took this picture from the textbook, it kind of bent the page a little bit, but that is supposed to be like an actual line. So sorry. So here's the equation of the model where T in hours is the time in which the battery is being charged. Always pause in an applications class and say, what does this make sense to me, right? What is my experience with charging a phone? Okay, I plug it in and it like starts charging really fast at first and it tends to slow down. This is like maybe something that we've heard about where they're trying to protect the battery's life by like, they don't want it to go like bam and hit fully charged because it wears down the battery, I think. So these are things that make sense to me that, yeah, my experience with charging batteries is that it does something like this. Okay, write down. So it should be super easy. Write down the amount of the electrical charge in the battery at T equals 0. T equals 0, we could just plug it in, but it does say write down, so it should be telling me that it's easy. But maybe this isn't easy to see because this guy isn't really written like our standard form up here. It might not be easy for you to see what K and C is, but we could totally just plug in 0 and then we'll make the connection later. Well, that's going to be 2.5 minus 1, which is 1.5. Okay. So my C value and my K value, the C value is the value that should be plus or minus, right? And so if I were to reorder this, that would be, remember that the sign always stays with the term that's behind it. So that would be negative 2 to the negative t, and then 2.5 is positive, so plus 2.5. So notice here that c is 2.5 and k is actually -1, which makes sense that adding those two together would actually turn into a subtraction, which now means that it's 1.5. Okay, if you were able to make that connection, awesome, for the shortcut and why it says write down. If not, you can still just plug in 0, right? You know what it means to be initial, just plug in 0. There's more than one way to solve these problems. The line L is the horizontal asymptote to the graph. Write down, okay, it should be in the equation. Write down the equation of L and explain what it means in the context of the problem. Go ahead and tell me what the horizontal asymptote is. Because of our rewording, I think you should be able to pull this out, or sorry, our reordering. You should be able to pull this out pretty quickly, right? It's this C value right here. We even wrote C equals 2.5. So our horizontal asymptote is Y equals 2.5. Explaining what it means in the context. This means that the graph will approach that 2.5, but it'll never go above 2.5. It might reach 2.5 in the application in the real world. Mathematically, no, but technically, yes, it'll probably reach 2.5. But what this really means in the context of the problem is that the battery will never go above 2.5. C, I guess, is the unit. No, 2.5. C is the variable. I don't know what the unit of measurements are. If you were not able to pull that out from the equation, if you had not been able to reorganize this equation, what's a way that you could have figured this out? You could have graphed the equation and just done graph trace and like tried to get as close as possible, see like, okay, what is the horizontal asymptote that I'm infinitely approaching but never crossing? There are ways for you to be able to problem solve this. If it doesn't work this way, try another way, right? Okay, if it's not working formulaically, try tangibly, try actually putting it into your graphing calculator and playing around with the numbers until something goes off. Okay, so it says to download the game on the mobile phone, an electrical charge of 2.4 units is needed. Find the time taken to reach this charge. Give your answer correct to the nearest minute. Do this on your own. Okay, so the charge is 2.4, so that means C equals 2.4. We want to find the time. Time is question mark, so 2.4 equals 2.5 minus 2 to the negative t. We could numerical solve this, or if we've already graphed it, we could do y equals 2.4 and then find that point of intersection. T will be approximately 3.32. T is in terms of hours. So to the nearest minute means I need to say 3 hours and something minutes. It's okay if the way that you problem solve is eventually just like taking it one piece at a time, right? Like 3.32 hours. That's 3 hours and put that down and then say, okay, how do I answer the right? Okay, well, that's not a full hour. That's 0.32 hours. That's not 32 minutes, my friends. Time with the 60s is weird. To figure out what 0.32 of an hour is, you have to do 0.32 times however many minutes are in an hour, which is 60. That's 19.2 minutes, which to the nearest minute would then be 19 minutes. So that would be the way to answer that question. Okay, good job today.